Let's now look at a particular model for realizing lexicalized PCFGs. And the model we're going to look at is the model of Eugene Charniak from Charniak 1997. This isn't the most recent model, but I'm choosing it because it's the simplest and most straightforward way of building a lexicalized PCFG. And so hopefully it's easy for you guys to get a sense of how it works. So just to give a bit of context for what I'm explaining, when you're actually parsing in Charniak's parsing model, the way he's doing the parsing is bottom up in a way somewhat similar to the way that we did CKY parsing in an earlier segment. But just as with a plain vanilla PCFG, the probabilistic conditioning is top down. So you've got the probability of a right-hand side given a left-hand side, i.e. the probability of stuff below given the stuff above. And in this segment, I'm basically just going to show you what the probability distributions are rather than actually concretely going through the parsing algorithm. But for the actual parsing algorithm, you're using these probabilities but applying them working upwards through the tree. So this is the idea of how Charniak's algorithm works. And for this example, what I'm going to assume is that this is our starting point where we're already partway through building a tree. So we have an S node and that we know the head word of the whole sentence is going to be rose. And that sentence is rewriting as a noun phrase and a verb phrase. Well, since the verb phrase is the head of the sentence, we just know automatically that its head word is also going to be rose. And the point at which we're up to is we haven't yet decided how to expand this noun phrase, and we don't know what the head of this noun phrase is. So in Charniak's model, there are two probability distributions that are used to expand out a sentence, and we'll see each of them in turn. So the first one is, G, we have to choose some head word for this noun phrase. And for choosing that head word, we're going to condition on several things. We're going to condition on the head word of the parent, the category, which is noun phrase, and the parent category, which here is S. And so the probability distribution we're going to use is this one. So we're going to have a probability over different head word choices given these three conditioning things: the category, the parent category, and the parent head word. And so what we're asking is, for a noun phrase which is in this context of being under an S node and having a head of the whole S be rose, what are likely nouns to choose as the head of the noun phrase? And so you might think of something like the balloon rose and say balloon, or temperature, temperature rose, or you might think tempers or something like this. But since actually here we're dealing with the financial newspaper, the Wall Street Journal, what it's actually likely to be, and is in this example, is that profits rose. Okay, so now we have this noun phrase here, which is a noun phrase headed by profits, but we don't actually know how it expands. And so now we're going to have a second probability distribution at work. And so we're going to want to have a rewrite rule that's working out how this expands. And what we're going to condition it on is the head word, profits, the category, noun phrase, and the parent category, which is S. And so that's then going to give us this second probability distribution here. What is the probability of a rule that expands us down one level in the tree given these three conditioning things: the category, the parent category, and the head word? Okay, so we're going to choose a rule. And so that rule could be just NP goes to a noun, a plural noun, and it would have some probability, or it could be something else. And so for this example here, the actual rule that's chosen is to generate an adjective and a plural noun. And so that's given by this probability here. Well, once we've generated an adjective and a plural noun, we then have the notion of a head of a phrase. So we know deterministically that if this is a noun phrase headed by profits, well, this plural noun must be profits because it is the head of the noun phrase. And since actually we're down to the level of a part of speech tag here, that means actually we have the word profits down at the bottom of the tree here. Okay, at this point, we've completed this element of the expansion according to these two probability distributions. And at that point, we're just going to keep on going. So we're going to say, well, here is a category. It's actually a non-terminal category, but we're going to expand that by working out what its head word is. So we're going to use this probability distribution, and we're going to choose a word here as the head word, corporate. And then by that point, because we're down to a non-terminal, we'll know that that's the word in the sentence. And then over here, the VP headed by rows, it's going to have to be expanded by making use of this probability distribution. So we're going to expand it and choose some expansion phrase. Maybe it'll go to a past tense verb and a prepositional phrase, and then we'll start expanding those down by choosing head words and how to expand them. We'll get the rows here automatically again, of course, which will then go to the word rows. And so that then we'd choose a head word over here and then start expanding it. So we're pretty much done. So the only thing we really need now is a way to get started. And so for that, we just need a slightly variant probability distribution at the beginning, so that we're going to say that we have a root category at the top and it needs a head word. So at that point, we're going to have a probability of a head word given that the category equals root. And then the other things, these don't exist. So this is just the chance of different words being the head of the whole sentence. And so then once we've done that, we can then start expanding downwards from there. So this will be a root headed by rows, and then we'll look for a rule to expand that. So we're now looking for some expansion, which will here just be to S under this. So at this point, we again don't yet have a parent category, but we've now got a category and a head. So you need a couple of special probability distributions to just get you started at the beginning, and then you do the basic recursion I've talked of here. So what do we achieve by putting these words into the grammar like this? So here are some statistics that show this, that go in a bit more detail what I talked about previously. So here we have different expansions of the verb phrase rule, and here we have a choice of different verbs for a head. And this just illustrates more systematically how the chance of different expansions for the verb phrase vary enormously depending on which verb you're choosing. So if you have a verb like come, you find out that getting a PP after the verb is enormously common. It happens about 1/3 of the time. And having just a verb in the verb phrase happens about 10% of the time. Where many other kinds of complements like S and NP complements are really rare with the verb come. But that's then exactly, and also with a noun phrase after it. But for other verbs, the facts are very different. So for the verb take, well, take normally takes an object. He took a nap, he took a book, he took a ticket, anything like that. So about 1/3 of the time, you get just VP goes to VNP. Though of course you can get other things as well. If we then move on to think, think is a sort of sentential complement verb that you're saying what you thought. And in fact, nearly always for think, almost 3/4 of the time, you're getting an S-bar complement. That's something like, he thinks that she is dishonest, he thinks she is dishonest. Either of those is an S-bar complement, regardless whether there's an overt that or not. And then the final example illustrated here is the verb want, which also takes complements, but it takes infinitive S complements. I want to go to the store. And so about 70% of the time you get that. And so essentially you notice that they're just extremely different probabilities of different expansions of the verb phrase, dependent on knowing what the head verb is. And this is precisely the kind of information that can be captured in the Charniak lexicalized parsing model. The one other final thing to note here is that these are what are sometimes referred to as monolexical probabilities. So we're looking at the expansion of categories in terms of the categories and knowing just one lexical item, the head verb. That's in slight contrast to the other main way in which lexicalized PCFGs are useful, and that's for predicting dependencies in things like prepositional phrases. So there we have bilexical probabilities. So that was when we had examples like go into or man with. We're then deciding how likely the connection is between a preposition and a noun or a verb. So these then involve two words at a time. So the Charniak model also has bilexical probabilities. So here are the chances of choosing the head noun of a noun phrase, a plural noun phrase, given some amount of information, which might include information about the noun phrase, but also information about what its parent category is and what the head word of the whole sentence is. And so what you find in the Wall Street Journal, this isn't typical of all English, is that if you have a plural noun, a bit over 1% of the time it's prices. But if you know that it's inside a noun phrase under an S node, i.e. it's the subject of the sentence, well then the chances of being prices become about 2.5%. But what really makes a big difference is that if you know that the verb is fell, well, that's information that tells you it's the kind of verb that could easily go with prices. And so then the probability becomes far higher again. So now it's up to almost a 15% chance, a 1 in 7 chance that the head of the noun phrase is going to be prices. And again, we're capturing a lot more of this probabilistic information. But you might be wondering now, gee, can we really estimate these probabilities? And the answer is that in general, you can't estimate these probabilities, that the probabilities that you'd like to estimate become far too sparse, and I'll illustrate that on the next slide. But the way that is dealt with in Charniak's model is by having a complicated scheme of doing linear interpolation between different models that are more or less precise. So this should be reminiscent of what you saw for language models in the second week of the class. So we want to estimate this probability distribution that we've seen before, choosing a head word based on the parent's head word, your current category, and the parent's category. And the way you're doing that is by taking this linear interpolation of a bunch of different distributions, that one of which is just the maximum likelihood estimation conditioning on everything, and then there are further distributions that first of all leave out what the parent head word is, and then also leave out even the parent category. So at this point you're just choosing a head word based on the category. So you're just saying it's a noun phrase, what's the chance of it having a certain head? And in Charniak's model, these different distributions are weighted in a deterministic way depending on how much you'd expect to have seen certain kinds of evidence. So making use of these language modeling-like techniques are essential to build these kind of lexicalized PCFGs because the data just is too sparse. And this next slide shows that. So here are the different distributions that are being combined together in the linear interpolation. So if we do the one on the right first, what we find out is that if you've got a noun phrase headed by profits, and inside it there's an adjective and you're wanting to ask what adjective it is, in the Wall Street Journal, about 1/4 of the time, it's corporate profits. Okay, so that's a very precise, fully conditioned estimate. Whereas when you start erasing some of the information, you get coarser but still non-zero estimates. I haven't actually mentioned this second line here. This was a method that Charniak used to get kind of coarse semantic classes to try and keep some information about the parent head word before getting rid of it entirely. But if we just don't really deal with that one and look at these two, you can see that once you're only conditioning on knowing it's a noun phrase under an S or just a noun phrase, the chance of it being corporate is then dropping by almost 2 orders of magnitude, so you're down to about 0.5%. Okay, so this is the good case in which you can calculate a probability from the rich conditioning and it helps you a lot. But quite commonly that just doesn't work for you. So if you then say, well, the verb of the sentence is rose, and I've got a subject noun phrase, a noun phrase under an S, and what noun should it be? Well, in the particular sentence in the data to be parsed, the actual noun was profits. But it turns out that in the training data, profits never occurred as the noun heading a noun phrase that was the subject of rose, despite the fact that that sounds perfectly normal. Profits rose last quarter, profits rose throughout the economy, any sentence like that. And so the maximum likelihood estimate, the MLE here, is just 0. And so the only way we're getting a non-zero probability estimate is by using these probabilities where we condition by less stuff. And even then, we're getting these low probabilities, right? So the probability of a noun being profits in a noun phrase, it's about sort of 1/20%. But that's the best kind of estimate that we have. And so although you'd like to use rich estimates as here, most of the time in doing lexicalized PCFG parsing, you're actually having to fall back on rather coarser estimates because you can't get the conditioning information you'd like to from the fairly small supervised tree banks that we have to train on. In particular, for these bilexical probabilities, when you're trying to condition on 2 lexical items, the probabilities tend to have to get backed off just because the amount of information to estimate this is extremely, extremely sparse, because you're in this space where even before you consider the categories that you're doing something that's kind of like bigram probability estimates, and it's hard to estimate word bigram probabilities on only about 1 million words of text, and that's all the text that we have in the hand-constructed tree banks. Okay, there were some details about the needed smoothing at the end there, but I hope the main thing that you could take away from this segment is how there was a fairly straightforward system of 2 probability distributions that Charniak was able to use to realize a lexicalized PCFG model.